Potential energy practice questions. Refer to the list of molar enthalpies of combustion in table 5.4. That's this one on over here. Write the balanced thermochemical equation for the combustion of methane gas. Okay, so I've already created the unbalanced chemical equation. How we're going to make it thermal? Obviously, we have to add this. Okay, where did I find that 890? Well, my methane is over here. Its standard molar enthalpy of combustion is negative 890.8 kilojoules per mole. So I'm going to add that over here. Okay, now how do I know if I put it on the right side or do I put it on the left side, on the reactant side? Okay, I'm going to be putting it on the right side over here. I'm going to make sure that it's negative, but I deem it as positive because this is going to be methodology number 1. If you have no idea what that means, see the previous video. Okay, representing enthalpy in 4 different ways. Link is in the description. So we have our potential energy on the side over here, increases going upwards, and we have our reaction progress going from left to right down here. Okay, so we're going to draw our reactants. Okay, oh, but we have to balance this chemical equation. So we have 2 over here, 2 over here. So we don't do anything with this 890.8 because we're just going to be dealing with 1 mole of the methane in question. So we have our methane. Okay, it's going to add with our oxygen. It's going to hit a certain threshold. Okay, the activated complex. It's going to hit that with enough sufficient energy and correct molecular orientation. It's going to make our product. Okay, so it's going to release a certain amount of energy. Okay, this much energy. What is the question asking for? We've already drawn our potential energy diagram, but we have to find a molecular structure that could represent an activated complex. So what would this be up there? Well, technically this is our reactant, but our reactant could also be up there as well because technically the reaction could proceed, okay, and the bonds can form, or it could go backwards and nothing could happen. Okay, it is possible. Next in this question, when steam is passed over, this reaction occurs. Obviously, same thing happens here, our PE and our reaction progress on the bottom here. And we have to put our reactants. Okay, so our reactants here is Fe, and then we have to put our H2O, which is over here. And that's going to, again, same thing. It's going to hit a certain activated complex. It's going to go down, become a product, and it's going to release energy. How do we know that our products are down here? It's lower than the reactants because the question does say that it is 151.2 kilojoules being released because it is a negative value. Okay, so energy is being released. So I could actually put that. Okay, our reactants are here, our products are here. You find the difference between that. It's just 151.2 kilojoules. Okay, now what else do we know? We know that the reverse reaction activation energy between the activated complex, okay, and our product over here is going to be what? It's going to be 200.71 kilojoules. Okay, so what's the question asking for? It's asking for the activation energy of the forward reaction. Well, if this whole thing here is 200.71 and this area here is 151, okay, if you find the difference between them, okay, we obviously have this little area here, and this is actually our activation energy, okay, between our reactant and the activated complex. So you find the difference between those, you get 49.51 kilojoules. So that is your answer, and we've already drawn it out for B. Try this question on your on the bottom, okay, and I'll give you the answers shortly. This is the answer.